Good afternoon, ladies and gentlemen. Thank you for joining us today for this webinar session on the interesting topic, Make Future Smart Batteries. This event is brought to you by the NTU Institute of Advanced Studies, the graduate student clubs of the School of Physical and Mathematical Sciences, the Electrical and Electronic Engineering, and the Materials Science and Engineering. My name is Shivam and I'll be your host for this webinar. Before we begin, there are some housekeeping rules for this webinar. All of your mics have been muted to prevent any accidental disturbance. If you'd like to ask any question during the Q&A session, please use the raise hand feature at the bottom of your Zoom screen. When your name is called, please ask your question. Or you can also post your questions under the Q&A feature at the bottom of your Zoom screen. For the postgrad students who require the endorsement of the attendance, please scan the feedback form at the end of the session and indicate the need for endorsement. Today's webinar is being organized as a part of the Discovery Science Seminars and Interviews Initiative. Let me introduce our speaker for today's webinar, Professor Fan Hongjin. Professor Fan completed his PhD from National University of Singapore about 18 years ago, following which he did his postdocs at Max Planck Institute of Microstructure Physics and the University of Cambridge. Currently, he is a full professor in the School of Physical and Mathematical Sciences at NTU. He is also the director of C.N. Young Scholars Program. He has received many accolades during his academic career. Since 2016, he has been recognized as a highly cited researcher by Climate Analytics. Recently, he became editor-in-chief for Materials Today Energy. Without further ado, let's welcome Prof Fan. Prof Fan, please.
Thank you very much, Shivan. And I would also like to thank IAS for inviting me to give this series seminars, as well as Discovery Science. They have contacted me a few times, and sometimes I forgot to respond. So I apologize again for the delay. So it's my great pleasure to have this chance to share our research, and some of it's not our research, but some is my observation from the literatures, and with postgraduate, with the students and research fellows and project officers in NTU working on electrochemistries and batteries. And so my topic title actually is very big: Make a future smart batteries. Battery can be smart in many different ways, right? And the different groups are working on different aspects of batteries, make it smart, make it, for example, safer, flexible, and high performance and low cost. So these achievements can make the battery smart in the futures. So let's start with the basic, the gut side of the lithium batteries, because the lithium batteries are dominating energy power unit for all the consumer electronics, as well as the electric scooters, drones, and some cars. A lot of cars actually, including they use both lithium batteries, sometimes also supercapacitors. So many different brands of cars actually are using batteries. Of course, the most famous one we know is Tesla, right? Tesla, they're developing their own batteries, okay, based on this three-phase NCM high nickel batteries. And the electric car in China company, the giant companies probably also know, they use the lithium iron phosphate. So it's a little bit old technology, but it's safer. Okay. So there's a diagram of the lithium battery. Change to laser. So there's a schematic diagram show how the lithium battery works. So the left side is a copper foil current collector with a graphite, which is the anode material. Okay. So there's a low voltage side. On the right side is aluminum foil current collector. Surface is coated with a slurry of this cathode material powders. And most of the research now is focused on this cathode side. Because anode side, there's not much we can do. It's just a graphite. It's the best material, it's cheaper, and it's a large scale, and it works very well. So we know that 3 years back, we have this Nobel Prize in chemistry given to the three gentlemen working on their whole life on lithium batteries. So these three guys work on different aspects. One's cathode, one is graphite anode, the other is put into batteries commercialized in installing companies. And then between the anode cathode, we have separators to separate anode cathode from the shot. And then within this whole thing is sort of soaked in an electrolyte. So for the current lithium batteries, the electrolyte is based on organic materials, solvents, organic materials. And this part, all the three parts is able to, has to work in good harmony, right? So if any of the three parts fail, not working well, then the whole battery will fail. So one of the major thing we know that how battery fail is a fire hazard, right? So for example, if you look at iPhone, the battery of iPhone actually, with the current iPhone 12, actually the battery capacity is not increased compared to this iPhone 7, right? For example, this is battery life. Look at the battery size, which is capacities, okay? And the battery, that's 11. Let's compare 11. 11 is a 3,000 plus milliampere per milliampere hour. So this is like a coulomb. So this is the amount of charge stored in the batteries. But it comes to 12. Actually, the battery actually become larger. If you open up, if you see the battery become larger, and the capacity becomes smaller. So probably I guess it's because they want to make the battery safer. Okay. But because of the smarter OS system, they can make a smarter use of the battery capacities, so it can last longer. However, the evil side of the lithium batteries is also obvious. I think you guys have seen this disasters. This is a Tesla car just blow into fire, just catch fire spontaneously and explode. This is in China. This is another battery, this electric scooter, suddenly catch fire in the lift. And unfortunately, there's 5 people in the lift, and including a baby. And then this whole thing happened just in 2 seconds. I believe that you also hear this in the recent news in Singapore, right? There's also a similar fire accidents by electric scooters that catch fire in the lift. And very often you may see your mobile phones like this, okay? The battery inside swell, and also this is even more often. I see this very, very commonly. You include those laptops put in your lab, controlling some equipments, and after 2 years, they swell like this. Some of my posters also show the laptop like this. I ask them to change the batteries immediately, okay? So this thing happens everywhere in the world, and then that's why the fire hazard sets a limit, sets a restriction for the lithium battery for the application in large scales, especially in aircrafts. So why the lithium battery can catch fire is, as I said, they can catch fire by different reasons. It can be lithium dendrite formation that punch through the cathode and anode side. It can be flawed separators. The separator is too thin, like the Samsung, right? The Samsung phones was all recalled because of the fire hazard, because they make the battery much thinner. It's so thin that the separator is too thin that they can punch through. The positive and negative side may touch each other, so catch fires. Overcharging, so that, for example, these electric scooters, if you put overnight charge, then it's overcharging. If they do not have a very smart temperature control, temperature management system, then they can catch fire and also cell crash. So if you go to more details reasons, go to the electrochemistry side. So the reasons that you can SER layer decomposition, all the battery cathode side has an SER layer, anode side also, the surface coating layer. If this layer is unstable, it releases gases, okay? This gas is generate gas inside, you can say that. That's why the whole cell will sweat. And the gas can also be generated by hydrocarbon from the lithium metal anode, okay? This is because of the lithium metals can react with the organic materials in the electrolyte and generate gases. And also the separator is not robust enough. So there's a short between the two positive and negative side and give you a very strong currents and the dual heat. So the dual heat will also heat up the electrolytes, generating gas. Okay, so the electron decomposition, the electrode itself, the cathode material itself may also be unstable. At high temperatures, if your cell goes to 180 degrees, then this electron material also unstable. They also release gases. Okay, so once they release gases, then the whole thing will swell and that generates a lot of heat in a short time. Okay. In addition to safeties, there's also a strong demand that the battery in the future should be made smaller, flexible, sometimes transparent. Okay, we can use one word. They say smarter. For example, in the traditional bulk electronics, we also have the battery. The battery can be big. This is no issue. But in the future, we have implantable sensors implant into your body. Smartphones like our iPhone 12, smart contact lens you put in your eyes, printable sensors that you can wear and put on your skin patches. All these tiny things. You want to make a battery also tiny, still high energy density, but also flexible, right? And if you open up iPhone 12, you can see the iPhone 12 now is much thicker compared to 10 or 7s. And actually, they can have a longer battery life. It's also because the battery actually takes a more volume of the whole iPhones. So the commercial flexible electronic actually currently lack a compatible flexible energy storage units. So actually, the development of the battery is slower compared to the development of the electronics. That's why a little bit strange, right? You can still, if the battery can be made very small and tiny, like a coin cell, you put a coin cell in your phones, you can imagine your phone can be made very small. Of course, that you also want to have a big screen, right? And very likely we need also high energy flexible batteries for all the electronic devices mentioned above. So the targets that says to all the battery manufacturers is that we want a battery that are safe and low cost, easy fabrication. Easy fabrication also part of the low cost. But safety actually is always the utmost important factors that people consider for certain applications, right? And high performance to price. Yeah, if the price can be lower and performance is the same, then it's also a big progress. And it can be compatible with the future electronics. As I mentioned, it's better to be the printable and flexibles. And alternatively, some batteries are not for those electronic consumables, but also for static energy storage, for wind, for solar, for tide, and for some mechanical vibration energy harvest. So if I harvest those energies, you want to store it, right? For example, in the future, a smart house, right? We want to have put solar cells in the top of the buildings for the daytime. But the daytime, we can just use electricity when electricity is not so expensive. But when the nighttime, the high peak area, we want to use this energy that we harvest from the sun. Then we have to need a unit to store the energy. So that's the batteries, okay, static one. So the solution for all these requirements for the targets is that we want to replace lithium to cheap metals, okay, cheaper metals, and also from flammable liquid electrolyte to aqueous electrolyte, water-based, okay, or to quasi-solid gel, salt gel-based, or to all solid. Everything from positive, negative current collectors as well as the electrolytes, all is solid. So the all solid batteries actually is now a very hot research topic in worldwide in all the research labs, and also from rigid to flexible. Okay. So if you look at this diagram, the current lithium batteries is the cathode material is lithium copper oxide. I think most of the lithium battery, iPhones, mobile phones, is based on lithium copper oxide. Okay, and they also lithium manganese oxide and lithium iron phosphate. So most of the bulky batteries for electric cars, especially for the China manufacturers, BRD is based on these materials. And anode materials is mainly graphite. Okay, there's also some commercial anode materials, lithium titanate, and also hard carbon. And then the organic electrolyte solution. In order to have a high capacity and safer batteries, so a lot of battery manufacturing, they improve the lithium battery by replacing the cathode material with a higher energy density, high voltage NCM or NCA. These are three metals oxide. An anode material to replace graphite with a silicon and tin based. It's still carbon, but put a little bit silicon and tin, less than 5%, the capacity will increase a lot. Still not enough. You want to go even higher energy densities, high capacity, even low cost, and especially safer. Then you have many other choices. All this battery in their circle lines have not been fully commercialized. Some of them is just started, okay, like a sodium battery, SIB. Sodium battery just started commercialization. Lithium sulfur batteries is under very intensive research. Lithium air batteries, so far, this guy gives the highest capacity. That means highest energy density compared to all batteries. However, this battery is very, very unlikely to be commercialized in a short time because that's the only, it has much more drawbacks compared to its advantages. And then it also have a multivalent ions. Compared to lithium, sodium, there's only one electron transfer. You can have a calcium, magnesium, zinc, aluminum. There's multivalent ions can give you high capacity. So all this battery, new generation battery, can make a solid state in order to make them safer. Okay. So all these are called post-lithium batteries. Okay. So there's a blossom of new batteries. If we want to replace lithium with a new metals, okay, we have a lithium, sodium, magnesium, potassium, zinc, aluminum. Okay, so when we want to replace it with new metals, we have to consider some factors. First is cost, how abundant they are in our Earth, and what is the price to find, or the price of the raw salt, because they do not come as element, they come as a salt, and also the fabrications, purification, things like that, and also the ionic radius. if you look at the periodic table, this material have a different ionic radius, right? And we will not just look at ionic radius. We look at the radius of ions, not just the atoms, right? So, for example, actually, aluminum, the ions is bigger, but the aluminum atom is bigger than lithium, but ions is much smaller. Okay, and also the relative potentials, specific capacities of the metals, as well as the proton material. If you put this material in the batteries, you have to consider suitable cathode and anode material. So you also have to make sure that you can find the partners that can work very well with them. So this diagram compares the annual output as well as the price. So the green bar represents the annual output. Oh, sorry, the green bar represents the price. Okay, the orange one, which is here, which you can't see for the lithium, is the annual output. You can imagine the annual output is so small compared to zinc and aluminum. And for zinc, aluminum, you even cannot see the green bar, which is the metal price. That means the price is extremely low. Okay, so that's why in this talk and in many research group, people are working on a sodium also. Sodium is between working on sodium batteries and zinc batteries. So far in industries, sodium batteries start to be commercialized to replace lithium, but the rest are all still in a bench in the lab. And the most promising one probably is zinc. Okay, and if you can put all these metal cations together to compare the ionic weight and cation radius as well as the hydrated radius, put them together to see which metal will be more promising. So why we care the hydrated radius? Because when the metal ions goes into the cathode modules, into the lattice, it's not just the atoms, it's not just cations. The cations are also surrounded by solvents molecules, so we call it hydrated radius. Okay. And these metals, magnesium, calcium, zinc, aluminum, can go to aqueous. Okay. The rest are still not so easy to go to aqueous. Ammonia battery or hydronium batteries can go to aqueous, actually, but these are not metal ones. So my talk will be mainly two parts. First part is sodium-based battery. Second part is zinc-based batteries. Okay. So why sodium? It's just cheaper, right? Easy. The answer to that question is very easy, just cheaper and more earth abundant. But then if you look at more detailed electrochemistry, we have to concern first is the ionic radius is larger, okay, 0.76 angstrom for lithium, 1.06 angstrom for sodium. So a larger ionic radius means that if you go to the lattice of the crystals, okay, it's not so easy for diffuse in and out, right? So diffusion become more sluggish. Okay, but the good thing is that abundant. And the electrochemistry for the battery mechanisms is quite similar, almost the same as the lithium battery, although the materials is different. Both positive and negative materials are different, but the electrochemistry work mechanism is basically the same. So people can learn a lot from the dominating batteries, electrochemistries. The anode will not be graphite. Okay, graphite is the commercial material for lithium battery, but not working for anode of sodium because the high ionization energies, so that when the sodium ions goes in, you will have a high energy barrier to intercalate. And also the sodium have a larger radius than lithium, much larger compared to the interlayer distance of the graphite. Okay, so that the corresponding capacity actually for intercalation is extremely small. Lithium is 370 something, right? But for sodium it's only 35. So people are using hard carbon. This is also the material used for commercial sodium batteries, hard carbons. So the capacity is 300 milliampere hour per gram, which is comparable to graphite for lithium. Okay. But the drawback is, as I mentioned just now, the sluggish diffusion of sodium ions because the radius is larger. So there also capacity loss at a high current. Why this consequence? Because if you want to, ions goes in a lot faster compared to fast charging and fast discharging, then ions cannot move in too fast. So it's become a limiting factors. So therefore, usually the sodium battery cannot have a very high charge discharging capabilities. And also, usually the electrode materials, especially cathode materials for sodium batteries, usually less conductive compared to the cathode material for lithium. So that even though you put those carbon additives, you may have to put more carbon conductive additives in order to improve. So this diagram compares more specifically the price between lithium and sodium. So overall, there's a 12% of reduction of price. And there's a very recent review on this big journal called the Nature Review Materials, super high impact factors. So this guy from Max Planck in Stuttgart reviewed the current status and the promise of sodium-based batteries. And according to this review, find there's already quite many startup companies working on developing sodium batteries. So all these different companies using hard carbon as anode material, but they use many different kind of versions of the cathode materials. Okay, and as well as that the electrode materials are organic. So now I'm going to show some examples that still in the laboratories, and some of the material actually also being used for the commercial company. One is NVOPF. Okay, this NVOPF is a typical materials later two-dimensional later materials for not two-dimensional. It's kind of a later structure that easy for sodium integration and deintegrations. But before us, there's no one realized the fabrication of a array structure means a direct growth of NVOPF materials on the current collectors. So we always use a solid-state diffusion, solid-state reaction mechanism to get powders and then mix with carbon additives and polymer glues. So in these papers, we first grow the vanadium oxide array structures on a three-dimensional graphite form. We use this as anode material. Then we take another step of the reactions, convert this vanadium oxide to this typical sodium vanadium phosphate materials. Okay, this is cathode materials. So this is what, before forget, this is what is in collaboration with Shen Zexiang in SPMX. And so we get anode, we get a cathode. Both is the strategies, the uniqueness here is that we grow the active materials directly on the three-dimensional graphite form as a current collectors. So we can assemble the full batteries. This is a so-called pouch cell, thin film batteries. And then we capture the battery like that. It's not like the conventional powder battery that have a very evident plateaus for discharging. However, there's more sloping discharge. That means it's more like a capacity behaviors. That's why we call the hybrid batteries. They can also light up LED, can light up electric fan, can light up whatever tiny electronic devices, and the cycle number 200. Actually, not that bad at high rates because 4 C rates is quite high compared to the commercial 1 C rate. Okay. So the mechanism here is that on the anode side, so this we want to emphasize that this is a strategy to realize a high C rates. High C rate means fast charging and fast discharging. For example, 20 C means 3 minutes. Okay, that means within 3 minutes the battery is fully charged. Of course, this battery is still thin film battery compared to the bulky ones. So why we can achieve the high rate fast charging discharge is because the different electrode architecture, battery architectures compared to commercial powders. So that on the anode side is a pseudo-capacitive anode. Okay, on the cathode side is integration cathode, but it also gives a very high rate performance because of the three-dimensional graphite form current collectors. So when they put them together, form a rocking chair batteries, sodium batteries, and then we'll find that both guys can give very high capacitive, which you can see from here, capacity behaviors, which gives you the high rate performance. Okay. And in a similar work, we use a very popular material called MOF, metal organic framework. Metal organic framework is a very is also kind of a god material that can have very wide range of applications. And people use it for energy storage and conversion, like electrocatalysis and energy storage. So in this work, we grow this MOF array structure like this on a carbon cloth. Cloth is like your clothes, but it's made of carbon. So this kind of cloth is made of a lot of carbon fibers. Okay, the fiber surface is densely covered with a grass-like MOF structures. And then after some treatment, we remove the metal ions, remove, and then we anneal them in argon, and then we convert this flakes into a porous carbon flakes. Okay, so this carbon flakes we can use as a three-dimensional current collectors, and then the surface we can deposit with by solution absorption reactions. We can get both anode materials as well as the cathode materials. Okay, as I mentioned in the previous slide. So this is just another way to realize the high rate performance using this MOF as a precursor. So as a result, we obtain this thin film battery. It's a cloth-based thin film batteries, and they are quite flexible. So we have videos in the paper to show the whole batteries It can fold, it can twist. Okay. And so this is the battery performance I mentioned. The mechanism is quite similar. So on the negative side is a supercapacitive vanadium oxide on the three-dimensional carbon flakes. On the right side is MVP, battery type cathode. So the whole battery is still rocking chair, but it's a hybrid battery mechanism because the whole battery manifests a capacity behavior. That means the voltage has a linear decrease with respect to the discharge time. So this is a typical feature of capacity behaviors. So it can bend, it can flat bend 90 degree or bend many times based on charge-to-charge curve doesn't change much. It can also run at 1 ampere per gram, which is a high current, to up to 2,000 cycles. Of course, it can also run at low currents, but low current takes a longer time to test, maybe take more than 3 months. Okay. So this is the cathode one, or this is the full battery one. So now I want to focus on the anode one, tin. So tin material is alloy type. Even in lithium battery, people explore the tin-based alloy type materials to replace the graphite. So for example, in this diagram shows that the anode side for sodium batteries, if we look at the sodium tin alloy, the capacity can be 800. Okay, can be 800. That means if you want to have a capacity match with the anode side, you don't have to give too much weight. You can use much less materials. Okay, make the electrode even thinner. So the commercial material I mentioned just now here is mainly hard carbons here. Okay, 200. Okay, but if you replace with a tin, it can be more than 800. But the problem of tin, which is a typical phenomenon for all alloy type, is the high expansion, volume expansion. So therefore, after a few cycles, they pulverize, they scattered, okay? They break into small particles and then cause a failure of the batteries. So people use all different kind of methods, strategies to improve the rate performance of this tin-based materials and the stabilities. If you look at the first article, Nature Communication 2016 from NTU, they got a very stable high rate. That means very fast charge and discharging capabilities of this tin monosulfide anode. Okay. The other work is from University of Wollongong, which is my friend Guo Zaiping. They grow this tin monosulfide particles. You can see these particles, granular particles, within the graphite, which is this three-dimensional graphite structures. And they find that, okay, this graphene can provide a very fast, like this schematic diagram, can provide very fast electron conduction path, and also can stabilize the whole tin monosulfide so that the capacity is actually higher and stable. And another one is also from NTU, from SCBE, my friend Xiongwen Lou. They also fabricate a nanotube structure of tin monosulfide and then cover surface with the carbon. Find that if you do not cover the carbon, okay, less than 40 cycles, the battery fail. But if you cover the whole surface with the carbon layer, they can run continuously up to 100 cycles. Okay, ladies and gentlemen, let's see. 200, 250, 100. No big deal, right? A battery will run less than this, maybe less than half a year. Then you have to replace battery. That's not what I want. So also 2 years ago, our group collaborated with Professor Rashid Rawa in NIE to extend the cycle life to 1,500 cycles rather than just 200. So how do you do? We'll still start with the tin monosulfide nanobelts. We'll grow hydrothermal methods, large grass-like structures. And then this one is not a big deal. Everybody can do it. A lot of reports already. And then you can either do a physical mixture with a conductive carbon, which is reduced graphene oxide, very popular materials to enhance the conductivity, to enhance the stability of many metal sulfide materials. This, we also did it. Still not good enough. Why? Because after many cycles, they still detach from the RGO. They also break into small pieces. And so that these particles of surface still coated with SCI layers. Very similar to the pure tin monosulfide. So what we do in our work together with Rashid Rawa is that we coat every single tin monosulfide surface with a layer of tiny graphene flakes, like a grass, so that it's like a spring comes in winter, in a springtime, that the whole surface, okay, is covered with leaves, okay. So with this structure design, the whole thing is conductive carbon, and also it's kind of wrapped around the whole surface there. After many cycles, the Tmonosulphite break into polycrystalline particles, but the particles still surrounded, encapsulated, or encompassed by the graphene glass or graphene surface coatings. And also, they will not form the HCl layer directly on the active material. Instead, they form on the outside surface of the graphene. We call it hierarchical graphenes. So that this kind of simple design actually have a lot of good outcomes. So I mentioned the method we realize this growth of the graphene is called the radio frequency plasma method, okay, which is a very powerful method to energy materials. You can have all different kind of gas plasmas. So the plasma has very high kinetic energies, can foster much faster reactions, commercial reactions, and also can have a very easy, facile surface modifications of carbon materials to induce defects. Okay, so in this world, first we have this Tmonosulphite nanobells, like the grass hairs. Okay, if you go to Mr. Barber's room, you can see this hair-like. And then after the growth of the hierarchical graphene surface by plasma method, all individual nanobells are covered with this hierarchical graphenes. If you go to TM, you can see this like this. Okay, this is the Tmonosulphite. This is the graphene structures, layered structures. Okay, and after the coating, the whole surface from about 30 micron thick film. Every surface is coated with this graphene surface. You can imagine that the whole surface become more conductive and stable. So indeed, if you take the pure Tmonosulphite, 20%, okay, capacity retentions, less than 500, less than 100, less than about, okay, this is 250. So less than 50 cycles, the battery fail. So if you physically mix with RGO, about 70%, okay, capacity retention after less than 600 cycles. But our design can extend to 1,500 cycles. Okay? So this is a detailed mechanism that will not go to details. Why? Not only cycle life, but also rate performance. It can go to 20 ampere per gram. This is a very high rate performance. Okay. So if you compare to all the other batteries based on tin-based or silicon-based materials, this is our performance. Okay. Although the current density, at all the different current density, the volume capacity can be very high. And we also look at what happens after many cycles. If you look at pure Tmonosulphite, the nanowires break into particle powders after just 5 cycles. But if you fix a mixture with RGO, okay, this is Tmonosulphite, this is RGO, you also don't see the original feature anymore. But this guy, okay, after even 250 cycles, you can still see the distinct features, right? All the nanowires inside probably become polycrystalline, okay? It's no longer single crystalline. But anyway, the individual wires warm is still there. Okay? So we'll not go to details why it can grow. Is because of there's a self-catalyst growth. The other one is about polarity switchables. I don't know whether you still remember there's a fire hazard. There's a fire accident about 2 or 3 years ago. I think it's 1 year ago, probably last year, yeah, during the circuit breaker period. There's a fire accident that in a lab that if you accidentally you connect the battery, when you want to measure batteries, charge and discharge, but if you connect in the opposite way, in the wrong way, then they could cause fire hazard. Yeah. So of course we know that even the car batteries cannot switch the polarities, right? Cannot swap. Otherwise, they do not work at all. Okay, the battery can fail. So people look at if a commercial supercapacitors, if the supercapacitor, if you look at supercapacitor, both cathode and anode are made of carbon. So if the material is the same, the reaction mechanism on the same on both sides, then there's no problems, right? It's just a physical absorption, desorption on 2 sides. There's no difference in the reaction mechanism, so there's no problems. So, but the capacitor has a rather low capacities. It's just used for the sports car starting out at the very beginning. It cannot last long. So what we're thinking in this world is that we can design a battery that can also swap the polarities, and it can also go to high overcharging discharging. So what we'll do in this world is that we fabricate a kind of amorphous beryllium oxide material. I mentioned this material just now, right? Which is amorphous compared to crystalline. And this material can have a sloping capacitive effect within a high voltage range from 1 volt to 4 volt. That means what? I can use the material for both high potential cathode, low potential anode. Okay. For example, you can measure the charge discharge within a high potential range, above 2.5 volt, or below 2.5 volt, low voltage range. Both have a very predominating, very evident sloping effect, or capacity effect. So that means you can use the material for high capacity, for the high potential side, as well as the low potential side. So that means the same material on both sides, we call it symmetric batteries. So this symmetric sodium battery is a collaboration with Professor Bustan, UCLA. This work is under revision. So this battery made and it can run 1,500 cycles with a nearly 100% cooling efficiency, very good, right? Energy efficiency is very high. It can go overcharge. Overcharge is disaster for your batteries. That's why all the phones and laptops, they do not allow you to overcharge. They have some kind of a smart control circuits to prevent the battery from overcharging. So that means when it shows a full charge, actually it's only 80%. But this battery can go to overcharge. You can go to over discharge. You can swap the polarity. You can also measure the self-discharge. That means you can just fully charge and put the battery there for 100 hours. There's nearly no difference. Okay. So this is a very interesting design. So that's what I talk about sodium batteries. Yeah. So far, sodium batteries, as I said, no big difference compared to lithium battery, except for the cheaper materials of sodium. Okay. And so what I had do before, we designed this kind of array type materials or surface coating methods to enhance the rate performance, to realize the fast charging, discharging, and also realize the high safeties by designing this symmetric batteries. Okay. So we realize high capacity and realize high safeties. So now come to zinc-ion batteries. So why zinc-ion batteries? Again, as I mentioned just now, we can compare the different properties of different metals: lithium, sodium, potassium, magnesium, calcium, zinc. All these metals are being investigated for these batteries. But then we look at this different things: standard overall potential, cost, abundancy, hydroated ionic radius, capacity, density, as well as specific capacities. Okay. So we have to find a good balance between the 5 or 6 descriptors. So this is what I mentioned just now, the important factors to consider. And so what are people doing for zinc batteries? That they can play all different kind of games for zinc batteries. Okay. And what I mentioned here, all is rechargeable. That means secondary, not primary battery you can buy from the 7-Eleven. So the popular aqueous rechargeable zinc batteries can be zinc-ion batteries. That is most people working now. A lot of Professor NTU also working now, NUS. Zinc magnesium flow batteries based on this kind of electrolytic process. Okay, electrolyte can flows inside. So you just provide current collectors. You don't have to coat the current collector with the active materials. Also, zinc-air batteries, most possible for commercializations because of the technology is very, very simple and facile, very cheap. However, there's not much room for improvement because this is mainly based on catalyst design. And also zinc-ion hybrid devices. That means it's a combination between battery and capacitive behavior to realize the high charge-discharge rates. People also can make this micro supercapacitor batteries for the flexible electronic devices. Okay, this one is very popular for this thin flexible devices. People also made this so-called fiber batteries. And in 2018, our group published the first review articles on advanced function material to summarize the so far available research on cathode, on anode, as well as on electrolyte of zinc-ion batteries. So we summarize different material like manganese-based, all this manganese-based, vanadium-based oxides, as well as the Prussian blue analogs. So this is organic inorganic hybrid materials. Okay. So all these materials are being used for cathode materials. Okay. So far, zinc-ion batteries has stimulated a huge interest everywhere, but because of the aqueous nature, aqueous means that it's just water-based. It's not like organic sodium is flammable. It's not flammable. And zinc, unlike lithium, unlike sodium, unlike potassium, they're flammable. Zinc, you can even eat it, right? You can go to big eater, you eat seafood, they also contains a lot of zinc. You can even smaller zinc battery will not cause dangers. But the key problems, there's also a lot of challenges. Key problem is that there's a lot of crystal polymorphs for magnesium, for vanadiums. The mechanism storage will be very different. And also the cathode stability is a big issue. That means this material are electrochemically unstable. They may dissolve into the waters. Okay? And also there's a failure, battery failure because of zinc dendrite growth and corrosion. So this is like metals. Most of the metal is in the aqueous solution. They have the dendrite growth because of inhomogeneous deposition of metal ions. And also corrosion. Corrosion means that you put a piece of zinc into a selected acid solution, you see bubbles, which is a hydrogen gas, right? So this may also happen in your batteries. If your battery is slightly acidic, then the zinc will be corroded and generating hydrogen gas. A big challenge for all aqueous-based batteries is the low operating voltage due to the water decomposition reaction. You know, water decomposition, thermodynamic energy limit is 1.23 volt. Considering the, let me see, I have the slides. Oh, I don't have that slide. Considering the overpotentials, let's say 1.8 volt. That means your battery cannot go beyond 1.8 volt. Luckily, by smart designs, nowadays lithium zinc-ion battery can go beyond 2.2 or even 3 volts by designing by regulating the electrolytes. That means not just pure water, they put some additives into the water, make the water molecules less active. So I show some examples of our research. This is also in 2008. We, again, very similar to the sodium battery before, we replace the conventional powder cathode materials and conventional zinc foil, just commercial foil, with array structures. Okay, we'll fabricate these array structures, cathode materials and zinc, to make the materials that can charge discharge much faster and also can cycle more stable, longer time. That means, let's say we can go to 50 C, we'll still have a very evident capacity here, rather than it goes to 0. And if we compare to all the batteries in the literatures, okay, compare to energy density, power densities, our zinc array, both array zinc batteries actually is here. Okay, will not win other groups in terms of power densities, but we can win in energy density at high power. Okay. The other example is this vanadium oxide. Okay, vanadium oxide, water, alkaline nanosheets. So we can use a hydrothermal method to grow very high dense network structures. This is a 2D structures. It's nanosheets. It's a high dense 3-dimensional porous. 3D porous is good. We can also go to high mass loadings. Okay, about 5 milligram per centimeter square. This is quite good mass loading, but not a very dense arrays. There's a porous, micro porous, so that electrolyte can still penetrate into the atoms. And the main achievement of this work is that we use intensive characterization tools to reveal the reaction mechanisms, how zinc ions goes in and out into the lattice. We have both in situ characterization and DFT calculations to reveal that there's a 2-stage reaction, redox reaction, vanadium 5 to vanadium 4, vanadium 4 to vanadium 3, to give a double of the peaks. Also give a double discharge plateaus of the full batteries. Okay. This also go to zinc organic batteries rather than use this inorganic, because inorganic is unstable, as I mentioned. After many cycles, they may dissolve. But what about replace organic? Organic materials, some of the organic materials can also be very stable in aqueous, as long as the molecules are designed, engineered in a way that they are stable in aqueous solution. So in this work, in collaboration with Professor Qishun Zhang, previously in MSc of NTU, now in City University of Hong Kong, they designed this kind of molecule, PDBs, contain this oxygen sulfur moieties, which can be electron donators during the discharge process. So that means if this guy can electron donators, and the electron can be captured by zinc ions, so that they can have a redox reaction. So this electron donating, the charge transfer reaction, if they're reversible, then this material can be used for batteries. So in principle, any materials, if it can have a reversible reaction, redox reactions, charge transfers, they can always be used for battery. It's just that stable or not, high or low capacities. So in this case, zinc ions can interact with both oxygen and sulfur. We'll call it ligands, okay? And We can also make this material to a polymer structure rather than just a single molecules. Okay, we can also make it into a polymers. That means a long chains. For example, this will have a 1, 2, 3, 4 units joined together. Okay, become a polymer. This polymer chains can rotate, bend. Okay, during the zinc uptake. So with zinc insert into the powders, into the bulk of this PDBs, the molecules inside can rotate. Okay, it's not so rigid structure. It can rotate. This is unlike the crystal structure of inorganic materials I mentioned previously, so that it can be used for this kind of flexible zinc batteries in the future. In addition to this battery mentioned just, we can also print. Rather than just use a hydrothermal growth, we can also print the batteries on a substrate. Okay. For example, this one will print the tungsten oxide, inkjet print the tungsten oxide on the surface of engineered zinc surface. Okay. Zinc surface, and then we have a layer of a sol gel, electrolyzed quartz solid, and then ink on the tungsten oxide. So tungsten oxide is a very typical material for electrochromic devices. That means you apply potentials, then the transmission become different. So that means if you make this as a battery, when the battery charge discharge, okay, there's redox reactions. The zinc ion goes in and out of the tungsten oxide. Make the tungsten oxide have a different valence structures, different valence states, corresponding to different optical transmissions. So it can work as first as a battery and also as electrochromic devices. So that means if you put your car windows made of these batteries, it can be a self-powered smart windows. Not only is inkjet printing, we can also print the battery on the papers. Okay, let's say you choose a paper. This paper can be just normal printing papers, or those are filter papers. But the paper is engineered with a hydrogel. Okay, so this is a hydrogel coated paper. So paper is made of those fibers. If you zoom into the papers, you see those kind of fiber structures. And then between the fibers, there's a lot of pores, a lot of micropores. So the micropores is embedded with the hydrogels, then the paper becomes stronger and more robust. So on this kind of engineered papers, on the top side and bottom side, we can use a doctor blade printing of anode and cathode materials. Okay. This one is in collaboration with my friend Sue Lee in NTU EEE. So this is battery structures, and this is scanning electron microscope of the cross section of the battery structure. This is cathode materials, which can be the manganese or can be nickel, and this is anode or can be zinc. So both are just you just make this. You just make the ink, right, and just print on the top and bottom surface of the hydrogel papers. You can also make the battery of different patterns. I mean, you can make any pattern because it's printed, right? And after this cathode anode, on the surface, you have to put current collectors. That means you have to connect with the wires, right? So we use gold foils as current collectors. So you may think, oh, gold is expensive. No. If you open up the iPhone, all these electron circuits, laptop inside, they all use gold as for some key components. They still use gold as connections. And this battery you put this one battery. This is 5 centimeters. 5 centimeters about this size. 5 times 5 centimeter thin film batteries. You can run this fan for 45 minutes. Okay, you can still continue to run 45 minutes. And during the time, you can also bend and twist the batteries. I even can cut it. Okay, we have experiment demonstration. Cut half, cut quarter, still working. Okay, no issues. For example, this is a bending test. Okay, and during the bending test, you can monitor the voltage change after many bending. You can bend 1,000 cycles of the thin film batteries, and the voltage, output voltage, has no big change. Okay. And thermal management. So we don't want a battery to get too hot, right? Although the current lithium battery can work and quite hot, sometimes you touch a mobile phone, especially if you put a mobile phone outside, it's too hot, and the sunshine, you feel the battery is very hot. Or if you watch videos, watch NBA, you get too hot. And the battery usually can work within a wide voltage range, lithium battery, let's say below 20 degrees, minus 20 to 60 degrees. But if it gets too hot, then it can catch fire, as I mentioned at the beginning. That's for organic. Okay, for water-based, they also have the same issues. If it's too cold, you can imagine that water gets 0 degree, it start to ice, right? Start to freeze, so it will not work. Okay, so that means people are doing all the different things to add some additives into the solutions. Anti-freezing, for example, if a car in China, in north part of China, right, the car will not work in the battery if it freezes. So you have to put a little bit additives to anti the freezing at low temperatures. And then, so in this work, we demonstrated a proof of concept of the heat management. That means, okay, we make this quasi solid state batteries using the sol gel electrolytes. Okay, sol gel is just like a transparent, like a rubber. You can pull, you can rotate, whatever. You put that materials contains water molecules and contains polymers inside. Okay, so water molecules can shuttle between the positive and negative electrolytes, provides the battery working mechanism. And then our anode and cathode side is made of those kind of foam structures. So the water molecules can evaporate, can also be absorbed into the batteries. So the whole battery can work at ambient conditions. So the idea is this: we design this kind of a hydrogel that if the temperature is too high, battery got too hot, then the water molecules will get evaporated. Okay, that means it's become concentration of the ions inside is higher. If the concentration is too high, then they're not so mobile, not so movable. Okay, so the ions will not become the zinc ions inside will not become less movable. So the battery will not work very well or not work at all. So it kind of protects the battery. When then the temperature cools down, the water can be reabsorbed into the sol gel, because sol gel can also capture water molecules into the cell, and then the molecules start to swim again. Okay, it's just like a fish swim in a clean water or swim in a dense water, a milk or something like this very dense liquid. It cannot swim freely, right? So that's the idea. It's a very concept demonstration. So ideas like this: that okay, you first charge the battery at 25-degree room temperature. Then we let the battery, put the battery at a high temperature, 50 degree. Not that high, right? If you go even higher, then the effect will be more obvious. So the battery the capacity increases first, but then decreases very sharply after some numbers. Okay, it's not dead. It's not like a battery dead. It's just asleep. Okay, and then if the temperature increases to 25 degree, after 3-hour recovery, the battery come back to life. Maybe after 6 hours, it fully come back to life. So you can see, the response is quite slow. Yes, the response is quite slow, and it's because of the polymer gel still not engine optimized yet. If someone can optimize the polymer gel or optimize the porous, the foam-like structures, the water can be easily evaporate faster and reabsorb. Then the response could be much faster. Okay, so we use two kind of PAM and PVA another materials to test the response. Okay, so have the similar response, but again, I say that the response time is too slow. Okay. I think it's about 1 hour. So the take-home message I cut my part 3 just now before the seminar. So the take-home message I want to show here is that sodium batteries are being commercialized to replace the lithium batteries, and they have a similar electrochemistries. Although the cathode materials, anode materials, and the electrolytes are slightly different. Okay, so it's quite promising. Aqueous zinc batteries are safer compared to lithium battery because it's liquid, it's water-based. It's still liquid. Lithium battery is also liquid. It's water-based, contains no flammable organic solvents. But the challenge is that because of water, the voltage cannot be too high. So far, the voltage mostly is about around 2 volt. If you want to go to 4 volt, like a lithium cathode module can go to easily 4 volt, 3.5 volt. Okay, for lithium phosphide, iron phosphate. Okay, lithium iron phosphate. For lithium copper phosphide can be above 3.5 or 3.8 volts. So therefore, you have to design some strategies to enhance the voltage, thus the energy densities output of zinc-ion batteries. And the battery can be made flexible, thin film battery, printed, okay, or can be also made printables, inkjet printing, 3D printing, dot blade printing. All this can be used for fabricating batteries. And battery can also be made multifunctionals to combine the batteries. And there's also a lot of ways going on, including our own lab, that we combine the batteries with a solar cell, combine batteries with a trouble electric generators. So trouble generators can harvest mechanical vibration from our environment. They have a lot of construction outside, right? Of NTU, every day is constructions, a lot of noise. And this noise can be harvested to generate electricity. And that electricity is AC current. And it can be stored in the batteries. Okay. And also people also connect batteries with some Wi-Fi devices, okay, to power the Wi-Fi devices. Okay. So that's all I want to share with you. So I'd like to thank all my students and posters that have contributed to this work: Cao Dongliang, Zhu Changrong, Yang Peihua, Song Ming, Tan Hua, Xue Tong, Jia Guicong, Sun Tao, and Wang Shenli, as well as collaborators. So actually, there's many more collaborators like research fellows. I did not put it in, but I put many PI. Shen Xiang, SPMS, Zhang Hua, previously MSc of NTU, now currently City of Hong Kong. Zhang Qishun also. Alex Yan, MSc, Liu Zheng, MSc, Liu Shuzhou, MSc. Liu Shuzhou did a lot of calculation for us. Bruce Dong, UCLA, and some professors, my friends in China universities. Okay. As well as a founding editor from Singapore Ministry of Education, Tier 1, Tier 2, as well as NTU SIP founding. So finally, just a few minutes about this journal. Today, there's a release of impact factor of new journals. Okay. Just 1 hour ago. I'm the current editor-in-chief of this journal, Material Today Energy. The current impact factor is 7.3. Okay, 7.3. The site score, which is based on Scoopus database, is 8.7. Next year, we are very confident we'll go beyond 10, the impact factors. So I put the 4R to describe this journal. We have a very responsible team. So probably not many NTU professors submitted this journal yet, but we, as an editor-in-chief, I look at every articles. I give sometimes a very lengthy, detailed instructions for authors how to make the papers more looks nicer. We have a very rigorous screening. More than 80%, maybe 85 or 90% of articles will be just returned. Let's use a nice word. Returned without sending to peer review. So you do have to send your high quality papers. If everybody just say I send my lousy paper to you, and while simultaneously I also hope this journal can go beyond 10. That's magic. It will not happen. So you have to send your high quality papers to us, and then next time we expect the impact factor to go beyond 10 quickly. We have a rapid publications, and so I process articles within a week. So people come into the system, I process it within a week, and then once accepted, the peer review process takes less than 1 month, sometimes 1 month, sometimes 1.5 months. And once accepted, it will appear online within 7 days. Okay. And we have a very reliable impact. Although impact factor now is not so high, but we have a very high reliable impact. So people know this journal is not so easy. People know the quality of the article in this journal is high. So submit your high quality paper to MT now. Thank you very much for your attention. Thank you.
Thank you, Prof Fan, for such an insightful talk. Now I would like to invite our co-host Shantanu from the School of Electrical and Electronic Engineering and Ernest from the School of Materials Science and Engineering to host the Q&A session.
Okay.
All right. Okay. Thank you, Shibam. All right. So just to let all the attendees know, for all attendees, if you would like to ask any questions, you guys can use the raise hand feature at the bottom of your Zoom screen. Alternatively, if you don't want to, you can also send your questions under the Q&A tab, and we'll get to you. So for right now, until the audience comes up with some questions or want to use the raise hand feature, will there be some questions from us to ask Prof Fan, Prof Fan regarding the journey of discovery and also all the materials. So without further ado, I'll just go to questions. So Prof Fan, actually the first question would be, yeah, so normally for traditional lithium ion batteries, we always the battery always suffer from low capabilities at low temperatures. So how do we actually solve this efficiency as part of all this smart battery novelty that has been ongoing for the others like sodium batteries and zinc batteries? Do they
Okay.
suffer from this problem also?
Yeah. Okay. Let's try to, because although we have not directly working on the wide temperature range of the batteries, but from what I know of the literatures, from what I understand from other groups, lithium batteries, solar battery can work at low temperature. This is no big issue. Sometimes just too slow. For example, if you charge batteries, it may not charge so fast. It's because the ions cannot move fast enough at low temperatures. Because we know that the ion diffusion of ions, especially if you go to quasi solid state or pure solid state batteries, then the ion movement will be much slower at low temperatures, right? That's why the battery will not charge fast. Right? And high temperatures usually brings more hazard, safety issues because of high temperatures. Then the cathode material is unstable. They release oxygens. They form metals. So decompose to metals and oxygens. And the organic solvent may become flammable. Okay. So for sodium batteries, it's quite similar to lithium. I think they can also work at low temperature, high temperature. There's no big issues because the electrochemistry is quite mature. It's quite similar to lithium battery. For zinc, it's an issue. Zinc is based on water based. So you can see, as I mentioned, just water may freeze at low temperatures. So people have add different type of the additives, add some oils, some salts, so that the water will not freeze. And the high temperature one, again, if temperature is too high, as long as below boiling waters, okay, probably still okay. But again, if the temperature is too high, some materials also become more dissolvable into the waters. Okay, manganese oxide, vanadium oxide of the metal organic framework, they may dissolve into the water directly at high temperatures. So that's why what you have to do is you coat the surface, you pacify the surface with a thin layer, inert layer that are more stable at high temperature, low temperatures. Okay, so that's been done by many groups.
Okay. Oh, there's just one curious question. So
Yeah.
in that case, have anyone actually heat up the battery at low temperature to make the battery to resolve all these ionic conductivity issues, like a smart heating mechanism, like all the smart materials? Is there something being done?
For those kind of very smart materials, yeah, people are okay, for safety study of batteries, people have to do both high temperature, low temperatures, as well as the punch throughs, the mechanical impact. Okay, so probably mechanical impact receives more attention compared to temperatures because most batteries will not work at extremely high temperatures, low temperatures. If you go to north part of China, Norway, Sweden, yes, that's a problem. But high temperatures is more serious issues. So yes, there are research going on, but most of the research put on the short of the batteries and the mechanical impact. Okay. For high temperature one, there is some research, yes, but as I said, for the high temperature operation, most of the research is try to improve the ion conductivities, stability of the cathode materials at high temperatures. Okay. Especially interface, all the batteries are interface. People know interface chemistry, physics, material science. So these are very cross-disciplinary issues. So the whole battery base is interface issues. Okay. So you have to control the interface reaction, interface stabilities, and in order to make sure the battery can work in a wide temperature range, wide pH range maybe, or and the mechanical impact.
I see. Okay, thank you, Prof, for that question. So actually, this question is that since that right now batteries are getting smarter in a way and we're heading towards like more technological advanced situation. So actually, how do we actually integrate all these batteries, like for future smart batteries in a way that are we able to let batteries know the device like can we communicate with another device in such a way that it can provide information to the user like, hey, the battery power is low, or the cycle length stability is no longer stable, or it
Very
also
interesting.
enable user to change the batteries in time. Yeah.
That's a very interesting question. A very inspiring questions. Yes, people are making the battery smarter. So let's look at the commercial battery first. The commercial batteries, consumable electronics is including cars. They have a very mature battery management system. Okay, BMS. So the battery management system basically manages the overcharging, discharging. So suddenly, let's say the current is too high or the temperature is too high, then they short the batteries. Because they put a lot of batteries in series, in parallel in series connection, right? Any of them fail. It will be, they put a lot of sensors, okay, to each batteries to sense the current, to sense the temperatures. Okay? If anything goes wrong, then the management system will, let's say, just like our fuse in a household circuit, right, will just stop the workings. Okay, and also they will prevent over discharge and overcharging. So we can only charge to 80%, can discharge, let's say, 5%. So protect batteries. But in the future, battery people will try to do is that they put also smart sensors. For example, they put a sensor inside the batteries, to sense the change of the, let's say, pH values, to change the currents, to monitor the currents, to sense the solvent concentrations like that. So before, even though the batteries swell like this, okay, but before the explosions, okay, before the fires, then you can stop the batteries. Okay? So actually, if you guys see phones and a laptop like this, you better stop using it and send to the for service and replacement. And but this one is unpredictable and sometimes unavoidable. So that means even the battery management system goes wrong. You do not. And this one, the electric scooter, probably I guess they may not have the battery management systems at all. Not like this. Otherwise, the price would be higher.
Oh, so Prof, since we are talking on this topic regarding the flammability of batteries, is there any way that we can make it such a way that incorporating fire retardant materials in batteries so that it sort of like prevent a fire or known so that people can get to safety before the thing explodes or catches fire? Is there such smart materials that could be done for this?
Perfect. Very good question. Yes. There are some people, not so many. There are some papers demonstrate the concept, the ideas that they put some fire retardant materials inside. Okay, so to protect, let's say, to protect cathode material to catch fire, or to protect or add some additive in the solutions, so the solution become less flammable, or just wrap up the whole batteries. Okay, the whole battery catch fire, but the whole thing will not be. The battery, let's say, goes to explosion or not catch fire. So such smart materials are being reported sparsely by some groups, but not so many work. But this is a very good idea. I think it's very hard to realize such materials. It's just that you either as the cost, as the weight, or the volume of the batteries. Okay, but probably it's worthwhile to do it.
I see.
Commercial batteries, there's no such thing, no such a smart materials
All right. Okay.
covering fire redundant cloth. Okay.
All right.
Packaging.
Okay. All right. So, Prof Fan, thanks. Meanwhile, I'll hand over to Shantanu from AAA GSC. He'll have some more questions regarding on the general aspect of batteries. So,
Yeah,
Shantanu,
we're happy to have answer more questions.
Thank you so much, Ernest, and thank you so much, Prof Fan, for that talk. I had a few questions, but in your talk, you in fact debunked a lot of myths that I thought were true. For example, about the overcharging of batteries. So I'll ask one question that wasn't addressed. Is regarding, it's great that batteries are getting smarter in terms of their capabilities, but how environmental friendly do you see these batteries being? And if not, like, what are the developments would you like to see in battery production to make it more environmental friendly?
Yeah, thank you very much for this very nice question again. So to make environmental friendly batteries, there's also multiple ways to do it, right? So that's why people now start to realize to recycle and reuse of the lithium batteries, to recycle the metal from the cathode, to recycle the graphite from the anode. Okay, but this recycling process itself can also be environmental unfriendly because they use a lot of acids. Okay, they use tons of acids to get a little bit of materials in outside, and they also produce a lot of waste. So as far as I know, there's also big research going on in NTU. I hope they have a good progress and can give us more hope that we can recycle the lithium batteries. On the other hand, we can also make future batteries using the earth abundant and greener materials. Okay, for example, not use those kind of highly expensive toxic elements. For example, if it is the NC and NCA, the materials now we're using, containing cobalt expensive materials, okay, and it's also toxic, right? So we want to replace the cobalt-based materials, replace less with the manganese, with the irons, which is cheaper. That's why lithium iron phosphate is a very reliable cathode material, although the energy density is not that high. And electrolyte replaced with because all these organic as EC, PC, this kind of materials are quite expensive so far. They're using for both lithium and sodium batteries. They're flammable. So if you want to make a future batteries less hazardous, then you can replace it with a water aqueous based. So that's why there's a lot of research interest going on for aqueous based batteries: magnesium, calcium, aluminum, zinc, potassium. Okay, for the environmental concern. So I think two sides. One is recycle and reuse, and using environmentally friendly method technologies. These are very, very, let's say, worthwhile to do that. And the second is use the materials that are more environmentally friendly for future batteries. Many years ago, people try to make carbon materials from the biomass. Of course, actual activity comes from biomass. For example, all these plants, fruits, skins, all this our life waste can be made of carbon materials, activated carbons or hard carbons can be used for batteries. And many years ago, people proposed to make organic batteries. Okay, so all the components will make organic materials, sometimes treated or not treated. But this so far, they are all in still concept yet. Still in research stage. Yeah. Indeed, sometimes when I throw away a lithium battery, I really feel guilty.
I read a note saying my audio wasn't too clear. Is it clear enough right now?
It's very clear to me.
Okay. My next question would be, so you mentioned how consumer electronics nowadays, they don't allow overcharging. First question would be, is that a material property that it does not allow overcharging, or is it just something that the manufacturers add into the battery management? And the second point is, if it is a material property, is it possible in the future for consumers to control the time it takes to charge batteries, so that you could just leave your phone charging overnight, but it doesn't damage the battery somehow?
Yeah. I think a lot of audience should know this very well. Just if they work on the batteries, because we can leave our phone for overseas charging, right? Overnight charging, right? This is no issues. That's what I'm doing very often. Although it's not advisable to do that, because these smartphones they have very complicated smart circuits, intelligent circuits to protect the batteries from overcharging. They will not charge to 80%. They will stop. And you can see that when the phone starts to charge at the beginning, it starts to get very hot. Okay, so ions move in and out. It's very high currents, moves very fast. But then after a certain stage, the voltage, because the first charge is voltage increase, and a certain stage of voltage keep constant. And after that, after let's say 60, 65, 70% charging, the voltage goes up, and the current will be different also at a different stage. So therefore, if you just leave a battery to a lousy charger without this CE, without this certificates, then you may cause hazard. You may cause overcharging. If the battery inside does not contain those circuits for protection, it may cause hazard. But for laptops, mobile phones, usually it's no problem, as long as I use. Sometimes the batteries, the charger is not a good charger. It's not from our main producers, manufacturers, or even your mobile phone. The battery is not provided by reliable manufacturers. They may cause issues. Okay? So sometimes I hear the explosion of laptop or mobile phones. It happens very rarely, but maybe it's because of the misuse by the users. And just now, the detailed mechanism of overcharging is that the material become unstable if the overcharge to high voltage, okay, or the anode side become unstable at a very low voltage. So that's why sometimes people are talking about deep discharge, right? Let's say a material have a 100% milliampere per gram capacity, but we're not able to use that capacity fully. We'll use only 80%, because if you use that much, 100% use of the capacity, we call deep discharge, then it also cause hazard. Okay? It's just like you cannot get yourself too hungry or too exhausted, right? You play basketball, don't play too long. 2 hours is okay. You can still survive tonight. If you get completely exhausted, you may have safety issues. I don't know.
Understood. Thank you so much, Prof. That's it. Those are the questions from my side. Over to you, Ernest.
All right. Okay. All right. Thank you, Shantanu. All right. So now I'll actually go through the questions from the audience. So we do have 4 questions in the Q&A section. So I'll just go through the questions. Before I go through, I'll just on behalf of the audience, would like to thank you for the wonderful presentation.
My great pleasure.
So, yeah. The first question actually comes from Christopher. You mentioned that on slide 10, you mentioned that lithium can sustain for 60 years more. So does that mean that there's only enough lithium on the whole Earth to last us only for the next 60 years?
Yeah. This is an estimation. Maybe more, maybe less. Maybe sometimes people find in a certain area, certain corner of the Earth, oh, there's a lot of lithium here, then it can sustain longer. But still, so far, the lithium is more, because if you look at the Earth crust, abundance of lithium and sodium is much higher than lithium. And also sodium can get from the sea waters. Why not?
Okay. So just actually to add on to that, so for instance, in the next few years, as more electric vehicles are being produced, as more countries switch to lithium battery, does that mean that this prediction of lithium will actually decrease? Instead of 60 years, maybe could it be like 40 years if we actually consume or produce more lithium batteries?
There is such a trend. I would say there's such a trend, although in the short term, it's not so obvious. Okay, less than 5 years, we still have lithium batteries in our phone, in our laptop, no issues. But maybe in the future, if the price, it adds to the price of your consumables, okay, the battery itself. Of course, the battery comes with every new design of the batteries. It comes with a patent, or it comes with a price. And if the price of the lithium goes up, then the whole battery, the whole consumables also goes up. Okay.
All right. So that means
electronic part actually it's cheaper and cheaper. If you open a phone, the electron becomes smaller and smaller and tiny. Actual price is cheaper and cheaper. But if the battery price is not coming down, then the whole thing is still get expensive. So expensive not just because the patents behind, and also because of the raw materials and the fabrication process and the laborers. So I think within 5 years, probably it's not so obvious. But let's say in a 10 years span, probably people have to replace with a lithium batteries.
Okay. So speaking of which, then we can actually go to a next question actually asked by Yijie. Actually, the question is that what kind of batteries actually show the most promising future of replacing lithium ion replacing the ion batteries?
Okay. It's hard to say. When I talk to people, they say that, okay, so far sodium batteries have been investigated, but the problem is sodium batteries cannot compete with the lithium battery in terms of energy and the power output. Power will be lower, that means charge will be slower. Energy density is lower, means that your car will not run as far as lithium batteries. Okay, so this is a challenge for sodium. And other batteries, actually they're still taking large market share is like lead acid batteries. Actually, most cars still use lead acid batteries, right?
Yeah.
It's not environment friendly, but as long as they're treated properly, not just throw away, it's still safe, right? If you do not touch the lead by your hand. So lead acid battery actually still dominating technologies. And also, of course, the battery mentioned now, this is not new. If we're talking about new battery in the future, okay, I would say magnesium and zinc are quite promising. Because they can make aqueous, they can make into aqueous. They can also, nowadays, the progress is very fast.
All right.
And zinc air is quite old technology. Recently, it's renewed because of the development of the catalyst. So rather than just use carbon as cathode materials or air cathode, now people put some more efficient catalyst on the carbon host to enhance the conversion efficiency, which is OR on the cathode side. So that if this is an old technology and zinc is much more cheaper compared to lithium, then I think it can also be commercialized. The other competing technology, including fuel cells, right? But fuel cell, again, is not a very new technology. It's just not largely commercialized. But fuel cell use hydrogen and oxygen, produce waters. It's also very competitive technology to lithium batteries.
I see.
For vehicles.
Okay, so Prof. So despite all the batteries I have mentioned about, so actually Ho Yong actually has one question also, which means the point that for electric vehicles, so what is the most promising type of battery that can be used for EV? Yeah. Yeah, which EV I think probably will be on power and range, I guess.
Yeah, so we know that all the electric vehicles so far are still lithium batteries plus supercapacitors, right? Buses in Switzerland using supercapacitors. Buses in China using lithium iron phosphate batteries and some with the supercapacitors. And cars from Tesla and BYD all is a lithium batteries. And some cars, sports cars from German, from Japan manufacturers start to use a fuel cells, but extremely expensive. Okay, because why? Because fuel cells have to use platinum. Platinum catalyst is more expensive than lithium. So needless to say, it's very hard to say for the moment which one will win out. Okay, again, depends on the price of the lithium battery, safety concern of safe regulation. Let's say if there's a policies, put some policy safety regulation that okay, we do not allow the personal vehicles use lithium batteries, then it will be replaced with other safer batteries. I think so far sodium will not replace it. Okay, because sodium just wins out in terms of price, but will not win out in terms of safeties. Probably fuel cell will be next alternative, I would say. But the battery mentioned here, let me say, the battery mentioned here, in the dash. So this is improved lithium batteries are being produced in the battery manufacturers, where all this one in dash circles are being researched, are being studied in the laboratories, not been commercialized yet. A little bit niche commercialization for sodium batteries, but still not large scale. So for the moment, yes, can't say which one will win out in terms of 10 years. Maybe still lithium batteries. People are talking about lithium metal batteries. Okay, so now lithium metal batteries is a big story, but I hope you guys know what is lithium battery means. That we replace graphite with a lithium. Okay, we don't use graphite, but use a pure lithium because pure lithium has an extremely high energy densities compared to graphite.
Yeah.
But the problem is that lithium has a dangerous issues, and use a lithium. It's more expensive. Right? Use more lithiums. I don't think the point of using lithium metal batteries actually, although there's huge research on it. Lithium ion batteries do not use lithium metals. Okay, it's just that the cathode material contains lithium, become a compound, contains a little bit lithium. provides the lithium in the solution to shuttle back and forth. The anode graphite does not contain lithium. So all the lithium comes from the graphite, from the positive cathode. But if you replace the lithium metal for the anode, then you need a lot of lithium metals, which is more expensive, and also have dendrite issues, more dangerous.
Okay. All right. Okay. So
that's why solid state. A lot of research is going on solid state. Solid state probably is kind of is a kind of balanced situation. Is balanced solutions for all these batteries. That if you make a solid state, okay, it becomes much safer. Not flammable, no dendrites, but then ions moves in and out, moves in through the solid state electrolyte is much slower. So probably you have to sacrifice the power performance of the solid state batteries.
Okay. Let's see. Okay. That's quite insightful, Prof. Okay, so actually, Prof, there is another question. So other than lithium-ion batteries, we also talked about aqueous batteries earlier, right?
Yeah.
So there is a question from Pierre who actually mentioned that what do you think about the prospect of aqueous aluminum-ion batteries? Because currently there seems to be no particularly suitable cathode materials.
Yeah.
Yeah.
I mentioned sodium batteries somewhere, aqueous sodium batteries. This one research is not so intensive compared to other batteries because it's not so easy. As I mentioned, not so many suitable materials for aluminum. So far the result, you can see that the anode one just aluminum, just aluminum metal foil. Cathode one, many graphite so far. Very simple, just use graphite or some other new compounds being discovered. And so cathode anode side, so maybe it's not a big deal. The big deal is the electrolyte. Aluminum does not come with a naked aluminum. It's not just aluminum 3,4. It has a surface surrounded by 4 big molecules. So make this aluminum ions quite big. So if there's a whole solvated ions goes in and out, it's not so easy also. That means the diffusion become also very sluggish. Okay. So this one do not have much choices in terms of cathode materials, in terms of the electroadditives to play with. Okay. Although I know that Stanford tried to set up a big program to commercialize their aluminum-ion batteries a few years ago, maybe more than 5 years ago. I didn't see any big progress for aluminum-ion batteries. For doing research, fundamental research, you can still do it, but it's not as much as you can do in terms of compared to zinc, calcium, magnesium, and sodium.
Okay. All right. Thank you, Prof.
Yeah.
This is actually quite insightful on aluminum batteries. Okay, so the next question actually is from Benjamin. So he mentioned that there's been a lot of advancements in battery technology described today. So you're seeing the Prof. So what do you think is the biggest challenge before we can see a rivalry between batteries and traditional power source like fossil fuel? Yeah.
Actually, I mentioned a little bit, maybe not so straightforward in the slides. So the major challenge, if you look at the targets, then we know that where is the challenge already. I would believe for the futures, the challenge mainly is still the high performance, price plus the safety, the two things. Okay, maybe sometimes we have to sacrifice the performance. Okay, I can remove this one, but low cost, price, and environmental. That means this does not produce too much carbon dioxide emissions. This will be win out. If you have some new technologies that it does not cost too much in terms of raw material, in terms of fabrication, you will not generate a lot of waste, you will not generate a lot of carbon dioxide emissions, then you'll be the good technologies. Although the performance is not that high. People, the mankind is always greedy, always want a new generation, faster, run faster. Why do you need it faster and faster, right? It doesn't have to be. You want a sports car to run at 150 miles per hour in Singapore? Not necessary, right? So sometimes you sacrifice a little bit power performance, energy performance, but you win out from cost, price, and environmental sustainabilities. It's still very good technology, I think. Yeah, but that's for the vehicles. But for printable, flexible electronics, things are different stories. For that ones, you have to be, the technology of the battery must be compatible with available fabrication technologies. Printing technology may be the best one. And for those IC fabrication technology from EEE, students from EEE know it, right? If you can make batteries in a large scale, completely automatic fabrication in large scale, then it will be also very useful. And if you make this battery in your tiny smart electronic circuits, electronics, then you also have to make sure they are bendable and wearable after many cycles. They will not leakage. You will not have your solutions electron leak onto your skin or inside the bodies. So for that one, safety is another concern.
Okay, all right. I see. Okay, so yeah, actually it's quite true. So also on the electronic side, we also have a question on that. So this question for Vivek Mohan. So the question is on one of the limiting factor for scaling up of electronic devices is the battery. So what kind of battery technologies in the future could help us realize a stickier, lighter and smaller batteries for application, such as for smartphone, EEG device, etc.?
Yeah. Our smartphones, EV, and flex electronics, this is a tiny one. It's two extreme. One is small and tiny. The other one actually is the other side is still bulky one. So if we make our batteries in the two categories, major category, one is bulk batteries. The other one is a small thin film batteries. Okay. So for bulky batteries, we want the battery to last long. That means energy density must be high enough. It doesn't have to be very high power. For certain applications, like for drones, the drones flies very fast, change directions, rotation very fast. That means you need very high powers. And currently, battery is already good enough for that purpose. So the power performance is already good enough. If you want even higher power for sports car, starting engine, right, very fast, then you need supercapacitors. It doesn't need a supercapacitor. It doesn't need batteries. It can be in series with supercapacitors, can give you power immediately fast. So I think for electric vehicles, the key issue maybe is not the power performance, but more energy densities. That means more charge per unit volume or per unit mass. Okay. And for those smart tiny electronics, then there's the other things. You want them safe and can also be it doesn't have to last very long. It can be, let's say, Wi-Fi charge, easily charge and discharge. And has to be robust, can be, let's say, how do you say it? After many cycles, the lifespan, okay, the lifespan must be long. Let's say if you plant some robot electronic device into your body, into your blood, into your body systems, you want the cell to be safe, it will not leakage, it will not break, okay, and it can sustain there for, let's say, for 5 years. Your heartbeat, what do you call it? Heartbeat breaker, those kind of things. For current technology, you have to replace the batteries after 5 years. So you don't want that to happen to your body, right? You want to implant it and then for 10 years or even longer. So that battery, you either let the battery life long, much longer, or you can just remote charge it. Just charge the batteries through your skin, okay, through your chest. That's make the battery smarter.
Okay.
So a lot of things are unknowns, but the future, I think, in a nutshell, the future in development of all the smart electronics are being restricted by the development of the batteries, the power units. Not necessarily batteries, sometimes is supercapacitors. Okay. So that's why there's another branch of research about supercapacitors, in addition to batteries, which can provide high power performance and also easier fabrications compared to batteries. Supercapacitor usually is very simple materials, cheap, carbon-based. And you will not use those kind of complex metal oxides. There's no dissolution issues. There's no fire hazards. The only drawback of supercapacitor is just it will not last very long. After one charging, it will not last very long. Yeah. For example, if you bus in a cities, if like small city in Singapore, every bus stop just takes, let's say, 5 minutes. Okay, the supercapacitor just runs out after 5 minutes, and go to the next bus stop. During the passenger loading and unloading, they will be recharged very fast. Because the recharge of supercapacitor is much faster, way faster compared to batteries. 10 minutes, fully charged, fine. Go to next stop, charge again. Okay.
Ooh, okay. Oh, sounds like the future will be quite exciting.
Yeah, there's a lot of challenges, but this is a battle that we have to do. We have to fight.
Okay. All right. So, Prof Fan, there's actually one last question. So, I think it's in relation to also the lithium supply. So, Jin Yan is asking a question that you have come across some recent news from Kais, if he's not mistaken, regarding the lithium extraction from seawater. So,
Okay.
he mentioned that despite the low concentration, would that be sufficient to overcome the scarcity of the amount of this lithium found in the ocean to make an impact on lithium supply? Yeah.
Yes, correct. There's some very interesting research to harvest or recover lithium from seawater. Seawater has a lot of things. You also have this heavy metals like platinum, PT, or palladium. So if you find a reliable technology, a viable technology to recycle those lithiums from seawaters, it will be very, very promising. So I think so far the technology is still, in terms of the price to do it, in terms of yield, is still not very promising. But everything starts hot, right? At the beginning, technology may not be mature enough. But as long as it's feasible in the future, I think it'll be very, very promising. So yes, harvest lithium from seawater is a very new idea, new technology, but it will be very, very, as long as it becomes viable and price-wise, in terms of price, in terms of environments, friendliness in the future, I think it will be very good technology. It's good that students pay attention to that.
Yeah, this week I have all the audience listening. I think it's a very interesting.
Platinum, all those radiative elements can also get from seawater.
Yeah. Okay, so I think from the Q&A session, I don't think there's any more question. So right now, I'll just move on and to mention that once again, thank you, Prof Fan, for answering all the questions, and also thank you for all the audience for patiently with us and also giving us such wonderful questions.
Okay.
So the next thing what we'll go to move on next will actually be the feedback form and so-called also the attendance sheet. So for all the audience, I would also like you to so-called go on to the next slide. All right, so yeah, so here's a QR code, and once again, thank you everyone for attending today's webinar, and thank you for fun for such a wonderful webinar today.
Thank you.
Yeah. So everyone, take care and stay safe, I guess. To all the researchers, all the best for your research, and Prof also, thank you and have a good day.
Thank you very much for this nice opportunity.
All right.
Thank you, Prof Fan.
Thank you.
Thank you, Prof Fan.